Today, I will talk about questions related to frameworks, also called geometric graphs. So essentially, those are graphs that the vertices are points in some Euclidean space, and the line segments and the edges correspond to line segments, and sometimes to more a general curve between these points. And they appeared in a variety of contexts. So let me start by mentioning 8 problems on coloring circles. Now, although I talk about coloring circles, you will easily identify that we are talking about a geometric graph, at least for some of these problems. And the first problem is quite famous, and stating it with circle make it a little bit more complicated. And here it is: consider a finite family of unit circles. What is the minimal number of colors needed to color the circles so that the two tangent circles are colored with different colors? Now, this is equivalent to the question, given a finite set of points in the plane, what is how many colors are needed to color it when points in unit distance are colored by different colors. And this is a famous problem, the Hadwiger-Nelson problem regarding the chromatic number of the plane. And recently, or a few years ago, Aubrey de Grey showed that the answer can be either 5, 6, or 7. It was known before that the answer is between 4 to 7, and he showed that he found an example of a unit distance graph that require more than 4 colors. This is a very nice problem. And here I stated it, the reason I stated it with circles that we will allow to discuss some more general problem. And the second problem is the same question, but when we also require the circles to be non-overlapping. And graphs which are obtained in this way are called sometimes penny graphs. And the answer is known to be 4. They are planar graphs, and therefore 4 colors suffice. But there are examples where you need the 4 color. And again, also here, you don't need the circles because this is just a question about a collection of points, where a framework where you consider the pairs of vertices of distance 1, and you assume that 1 is the minimal distance between different vertices. Now we can replace the role of minimal and maximal, and we can ask the same question with pairwise intersecting circles. So in this case, we have a collection of points. We assume that the maximal distance is 1, and we connect with an edge the pairs of points of distance 1. And here it's known that the answer is 3. You need only 3 colors. And this is a finite version of the planar Bourseau problem that I will mention a bit later. And the reason I talked about general circles and not only about unit distances is that we can change this problem to consider circles with different radii. So the next question is similar to the penny graphs, but this time we allow non-overlapping, but not necessarily unit circles, non-overlapping circles. So we consider non-overlapping circles of arbitrary radii, and we ask, and we we describe a graph where the vertices correspond to the circles and two vertices are adjacent if the circles are tangent. And in this case, there is a theorem by Kebe. It's easy to see that every such graph is planar, and there is a theorem by Kebe that every planar graph can be realized in this way. And okay, so in this case, the number of colors required is a famous problem. This is the four-color theorem. Now we can ask, what happened if we consider circles and this time we have no condition, not that they are overlapping, not that they are intersecting, but the edges between the vertices correspond to the circles, and two circles are connected with an edge, are adjacent if they are tangent. And in this case, we don't know in this case, we know, actually, this was shown to me by Ron Pinchasi, that there are examples where you need where you require log n colors. And he also showed that you don't need more than log square n color. And this is it's an interesting question to understand this situation. But now we can ask the same question and add one more condition. And the condition is that every point is included in at most two circles. So again, we have a collection of circles in the plane. This time we don't assume neither they are non-overlapping, nor that they are intersecting, but we assume that every point in the plane is included in at most two of the circles, and a Ringel conjecture, and this is still open, that a finite number of colors suffice. And this is an interesting conjecture, which is open for many degrees. And another question, we can ask the same question for pairwise intersecting circles. So this extends the question we asked earlier about graphs of unit distances, where all the distances are smaller than one, where one is the maximum distance. And here I don't know the answer. So this is an interesting question. What is the maximum colors needed to color a collection of pairwise intersecting circles where you declare two circles adjacent if they are tangent. And another very interesting question is to replace the notion of circles by pseudo-circles. And now we can ask about pseudo-circles, and we can redefine the notion of adjacency. So one natural definition is to require that to say that two pseudo-circles are adjacent if the lengths that they determine. You see here, here you see two pseudo-circles, and this is this area is called the length. If the length is empty and does not contain any other point, and it's not known if under this condition a finite number of colors is sufficient for coloring. And for all of these problems, there are interesting questions regarding the maximum number of edges. Sorry, this is a mistake. The maximum number of edges. Sometimes the result about maximum number of edges gives some indication about the chromatic number, and this is quite interesting as well. And there is one case, so we can consider unit distance graphs, a unit distance graph where one is the minimum distance, and unit distance graph when one is the maximum distance. And the third question about a unit distance graph where one is the maximum distance, there is a famous theorem that asserts that the number of edges is at most n. So another way to say it, let G be a planar geometric graph framework. If the number of edges is larger than the number n, okay, so I'm sorry, this is not the way to say it. This is slightly more general theorem. If we have a planar geometric graph, and if we have more edges than vertices, then the graph contains two disjoint edges. Now, for when we have a unit distance graph, and the one is the maximum distance, we cannot have two disjoint edges, because we will have one diagonal where the distance must be larger than one. So this result by Hopp and Ranevitz, which is a very interesting result on its own, imply the result about unit distance graph where all the distances are smaller than one. And it is a starting point for a lot of work involving both essentially geometric graphs in the plane and in higher dimension. And let me show you a proof for this result, which is due to by Micha Perlet, and it uses an interesting technique. It uses lice. So here is the proof by lice by Micha Perlet. So I should define what is a louse. So I will rely on some general knowledge that you might have. So a louse lives on a head and wishes to lay an egg on a hair. So when we consider geometric graphs, we consider every vertex of the graph as a little head, and every edge connecting two vertices as a hair. And now I will describe the proof of the theorem that a planar geometric graph, when the number of edges is larger than the number of vertices, contain two disjoint edges. So the proof is based on a process of three parts. The first three steps. The first step is to take n lies. You take n lies from your head and put them on the n vertices of the graph. In step number 2, each louse examine each edge or hair coming from its vertex head and lays an egg if possible. I will soon tell you when it is possible and when it is not possible. And the third step of the proof, you take back the lies and put them back on your hair. And to have this proof work, we need a special type of lies called the spoiled left wing louse. And I will mention that also a spoiled right wing louse can also be used. Now, what is a spoiled left wing louse? It's a louse that lays an egg only if the area near the head is free from other hairs 180 degrees to the left. So here is a picture. Here you see a little head and a louse on this head. And in this head, there are two hairs or two edges coming from it. On this edge, it is okay to lay an egg because the whole area of 180 degrees is free from other hairs. On this edge, it's not okay because here, if we look 180 degrees, we see that this should be to the right. Stay to the right. Okay, So here it's not okay on this hair, and it's okay here. Here, if there is a vertex with 3 edges going from it in this way, then the poor louse on this head will not be able to lay even a single egg. And the simple lemma is that every louse lays at most 1 egg. Although the louse examine all the edges coming from this vertex, you see that if it's okay, so if it's okay to lay an egg on this edge, this means that all this area is free. And then if there is another edge, it should be in this area, but then like in this picture, it will not be okay to lay an egg on this additional edge. So it is at most one, every louse can lay at most 1 egg, and in some cases, not even 1. Okay, now we prove the theorem, the Hopf and Pantwitz theorem, and the way we prove, we know that there are n+1 edges and only n vertices, and there is an edge with no eggs, that no eggs was laid on this edge. So we look at this edge, let's call it X, and we ask ourselves, why is it the case that the lice sitting in this vertex didn't lay an egg on this edge? And the reason is that there was something 180 degrees to the right that interfered, and this was this edge. And why is it the case that the louse sitting on this vertex didn't lay an egg here? Because some edge interferes in this 180-degree angle. So these 2 red edges that demonstrate why an egg was not laid are disjoint. And as a matter of fact, not only that you get 2 disjoint edges, you get a configuration of 3 edges that can be called a zig. So it is a configuration like this with the same orientation as this picture. And if you use right-wing spoiled lice rather than left-wing spoiled lice, you get the mirror image of this configuration. You get zag, which is something like this. Trace it with another. Okay, so this is a very simple proof. As I said, this is the beginning of a very nice theory of geometric graphs with extremal questions of this nature. And I should mention that the topological version of the Hopf-Pantwitz theorem is the infamous Conway's Thrakel conjecture. So what Conway did, he replaced a line segment by pseudo-line segment. So a Thrakel is a collection of n points in the plane and some curves between pairs of these points, so that every 2 edges meet precisely once. And the conjecture is that in such a configuration, the number of edges is also smaller or equal to the number of vertices. Sorry. And this is a very famous open problem that many people tried, and it's very elementary to state. One can see that you can realize with Thrakels more graphs than you can realize with line segments. For example, with line segments, you can realize only odd polygons like this. Like something like this, but when it comes to curves, you can also realize even polygons. So you realize more graphs with n edges, but not at least with more than 6 vertices, but not. As far as we know, there are no examples you can realize more than n+1 edges, and this is the conjecture. Okay, I mentioned a little bit the Borsuk problem, which is related to unit distance graphs or frameworks in high dimension. And let me make this definition. F of D is the smallest number such that every set of diameter 1 in RD can be covered by F of D sets of smaller diameter. And let me also mention a related function, which is G of D. This is the smallest number such that every finite set of diameter 1 in RD can be covered by G of D sets of smaller diameter. It's not known that F of D is equal to G of D. From time to time, people send me proof that these two numbers are the same, using some arguments like compactness, something like that, but usually these proofs are incorrect. So although I tend to be convinced, but eventually they don't work. And it may well be the case that these two functions are not the same. But Borsuk asks, is it the case that F of D is equal to D plus 1? So is it the case that every set of diameter 1 in RD can be covered by F of D sets of smaller diameter? And this is a very nice problem. And of course, if F of D is, in cases where F of D is equal to D plus 1, also G of D is equal to D plus 1, because because G of D is always greater or equal to D plus 1 as seen by the vertices of the regular simplex. So the regular simplex shows us that the G of D is greater or equal to D plus 1. And another relevant example is the example of the ball. The unit ball, which is volume-wise the largest set of diameter 1, well, it's not the unit ball, but the ball with radius 1/2, it's the largest set of diameter 1. It can be divided into D plus 1 sets of smaller diameter. And famously, the Volcolam Theorem that I mentioned in the first lecture asserts, in some of its equivalent form, that you cannot divide the unit ball into D sets of smaller diameter. Or another way to say it, if you divide the unit ball to D sets, let's say D closed set, then, okay, to D sets, then one of these sets has diameter 1. So if these sets are compact, then one of these sets contains 2 antipodal points, which is a well-known version of the Volcolam theorem. So since the ball is the largest in some sense, Borsuk asks if it is the case that F of D is equal to D plus 1. And with Jeff Kahn, we proved that F of D is greater than 1.2 to the D. And we also show that F of D is greater than D plus 1 when D is equal to 1,325, and also to all dimensions greater than 2,000. And earlier, there were two upper bounds on the Borsuk number. One was by Lassak, who proved that F of D is less than 2 to the D minus 1 plus 1. Very nice proof. And another one by Uded Shram, who proved that F of D is smaller than the square root of 3 over 2 plus little of 1 to the power of D. And I'll say a few words about this, about the Shram's upper bound, but oh, I'm sorry, there's a mistake here. What we proved is that F of D is greater to 1.2 to the power square root of D. Let me emphasize this, a square root of D. Yes. It is an exponential behavior, but we don't know if the exponent is d or square root of d. And so far, there was a slight improvement or some improvement in the 1/2 term was reduced a little bit. But as far as we know, but so far we were not been able to improve the square root d term. Although it's commonly conjecture that the truth is fully exponential. That so a conjecture is that f of d is greater or equal to some 1 plus delta to the power of d. But this is not known, and nothing better than square root d is known. Also regarding the upper bound, Oded Schramm upper bound of square root 3 divided by square root 2 plus little of 1 to the power of d is asymptotically best possible. There was an attempt to attack this problem in a different direction by Bourgain and Lindenstrauss, but they came out eventually with the same bound. So Oded Schramm proved that if you start with a set of constant widths, you can cover it by this number of sets, which are of smaller homotets. And Bourgain and Lindenstrauss showed that you can cover every set of diameter 1 with this number of sets, which are balls of diameter 1, smaller than 1, doesn't matter. And although we have 2 proofs for the same bound, we don't know how to improve this concept. And I should mention that Bondarenko proved that found the 2 distant sets in R65, which violates Borsuk conjecture. And this is the world record as far as the dimension is concerned. So Oded Schramm used in his upper bound, he studied sets of constant width in Euclidean spaces and spherical sets of constant width. And I'm sure you all know what are sets of constant width and the Rayleigh triangle. And there is also a famous story why the existence of sets of constant width might have been the reason for the Challenger disaster, although I will not tell you this story today. But certainly they are very exciting geometric objects. And Oded Schramm asked both for the Euclidean geometry and for the spherical geometry, are there sets in RD with constant width 1, so that the volume of the set is smaller than 1 minus epsilon to the power of d times the volume of a ball of constant width 1. So we know that there are sets of constant widths which are not balls. This might be a big surprise. It is certainly many people, including mathematicians, are not aware of this fact. But the question is, when we go to larger and larger dimensions, are there sets of constant width with volume which is exponentially smaller than the volume of a ball? And this is not known. A positive answer, a negative answer to this question for the spherical case may improve, will improve the upper bound of Oded Schramm from square root 3/2 to square root 4/3. But the truth of the matter is, I don't have a guess if there are such a set of constant widths or not. But what I want to tell you mainly about Borsuk conjecture is how to save the conjecture. I think once you disprove a conjecture, you have some moral obligation to save it, namely to find statement which will make the conjecture still correct. And once you prove a conjecture, then you need to pose a stronger conjecture. It might be incorrect. So this is necessary so that we'll have a sufficient flow of conjectures. That and yeah, I think as somebody mentioned in the chat, Genrich, and I forgot to mention, improved, I think, by one the dimension of Bondarenko counterexample, and now he has the world record. And earlier there were also exciting construction based on the Leach lattice. So here is the conjecture, and I will state the conjecture mainly for the finite version of Borsuk problem, but you can also extend it to smooth to bodies which are not convex hollow finite set of points. But for finite set of points, it goes as follows. Consider a framework F in RD such that the edges have distance 1 and the non-edges have distance smaller than 1. So far, it's the same as the Borsuk, the finite Borsuk problem. But now we add another condition. If F is stress-free, then F can be colored by D+1 colors. Or another way, if F is stress-free, then the vertices can be divided to a D+1 set of smaller diameter. So just to remind you what is a stress, so probably most of you know it better than me, but a stress on a geometric graph is some assignment of weights to the edges so that every point is in equilibrium. So to say that if configuration is stress-free means that this construction is not a coincidental construction. So there's several ways to reformulate it and also to extend it to the non-finite case. We want to say if we slightly change the one distances, we can still change the framework and realize the new distances. So for example, this is one way to say that it's stressful. In any case, here, this is the conjecture. So this is a conjecture of very different nature because the number of edges in a stress-free framework is at most, as you know, d times n minus d+1 choose 2. So there will always be a vertex of degree 2d, and therefore the number of colors needed is at most 2d. So here the task is we don't have a exponential number of colors needed, but the task is to improve this 2D. Let me change this color. Not be part of the conjecture. I learned to do it only today. I'm very proud of myself. So this is a nice extension of a Borsuk problem. And I should say that Borsuk problem is open in dimension 4, and it would be nice to prove this in dimension 4. Actually, I would be interested to see what happens in dimension 3. Although it's known that the Borsuk conjecture is correct in dimension 3, I would like to understand why this particular version is. Okay, so I want to mention some problem on rigidity. Let me say a few more things about no, let me go on to talk about a problem in rigidity, and I want to emphasize one problem which, so as I said, there are some very nice connections between rigidity of frameworks and between convex polytope theory. And I also expect connection with Helly-type theorems that I mentioned in the second lecture. I know a few of them, but not so many. And let me mention some problems regarding rigidity. And the first problem I want to mention is to extend Whiteley's theorem for polyhedral spheres. So let me remind you Whiteley or Alexandrov Whiteley's theorem, and it is the following. So we have a P is a D polytope. And now we consider a framework where we triangulate the two faces of P with no new vertices. So every time we have a two face of P, we add diagonals, or it's a simple way to say it. We triangulate the two faces of P with diagonals, with non-crossing diagonals. And then the theorems assert that P is, okay, this framework, so let's call it F of P. F of P is infinitesimally rigid. And I think I mentioned then result, which said the simplicity polytopes in free space are simplicity rigid. So even in free space, this is more general than then result. I think in 3 dimension, it's due to Alexandrov. And the proof in higher dimension is very ingenious, Whiteley proof. And I can tell you the basic idea. The basic idea is that when you can consider, okay, let's take Alexandrov result in dimension 3 for granted. Let's prove it by induction. And by induction, if you add all the edges among vertices of a facet, of a d-1 dimensional facet, then this does not, then if the resulting framework is infinitesimally rigid, then the original framework is infinitesimally rigid because you only added edges which belong to the circuit of the infinitesimal rigidity matrix. So the first step is to add many more edges between every two vertices which belong to the same facet. Once you do this, you notice that the link of a vertex or even a framework based on the link of the vertices is embedded inside your new large framework. And therefore, again by induction, this link is d-1 rigid, and the cone over it is d-rigid, is infinitesimally d-rigid. And therefore, after you take the framework, you add many more edges, you identify the links of the vertex figures, actually, the vertex figures of each vertex inside this large framework. And this vertex figure is d-1 with, when you triangulate the two-dimensional faces, is d-1 rigid. Then you use the cone lemma that when you add the additional vertex, the resulting subgraph is d-rigid. And then you have sufficiently many pieces of d-rigid subgraphs with large intersections that allow you to conclude that the full framework is rigid, infinitesimally rigid. So this is a very beautiful result. And one frustrating thing about this theorem, one frustrating thing about this theorem is that the question. So this implies that the frameworks, such frameworks based on deep polytopes, are generically rigid. And the big question that I want to emphasize, though I mentioned it, is it true? It's true. So the generic rigidity for a spherical, for polyhedral sphere. And actually, we expect it to be true not only for polyhedral sphere, but also for regular, say, strongly regular, strongly regular spheres and manifolds and pseudo-manifolds. So this should hold in greater generality, but we don't know it for polyhedral spheres, even in dimension 4. So D = 4. So this is a problem which is quite central in this theory. And if the answer is yes, which I'm sure it is, then this would lead to a complete understanding of phase numbers of polyhedral spheres. So this is a very important question, and I would like to emphasize it. So let me mention another problem, which is there a Kelly-type formula for minimally rigid graphs? So we know that, so we know that the number of level trees is n to the power n minus 1. Now, a famous way to prove a Kelly formula, although not the simplest way, is to look at the following. We look at the graphic metroid. So we look at the incidence matrix. So here we have the edges, E1 to E n choose 2. Here we have the vertex 1 to n. And here we have, whenever we have an edge, we put 1 and minus 1 to the edge, to its vertices. So this is the signed incidence. This is the signed incidence fix. It has rank n minus 1, and therefore we delete one row, and we get a n minus 1 by n choose 2 matrix, which is, we can call it the reduced incidence matrix. Let's call it I star. And then we look at the I star times I star transpose and look at the determinant. And this determinant is by a Cauchy-Binet formula. This is the sum of all A square, or that A square, where A is a n minus 1 by n minus 1 submatrix. And these submatrices contribute 0 or plus minus 1 according to whether the columns are cyclic, hence trees, or not. So this is the matrix tree theorem, and it allows, when you look at when you look at the complete graph, it gives you a proof of Kelly formula. And this is something we can imitate for a rigidity matroid. So I should say that so what we can do is, instead of looking at this matrix of the graphic matroid, we can look at the matrix. So now we have a matrix, again, n choose 2. Let's say we take d equal 2 for simplicity. And we look at the, here 2d. So in this case, every vertex, every vertex contribute 2 rows, but as we know, the rank of this matrix, and here we can use either the rigidity matroid matrix or some variant of it, or Whiteley matroid or hyperconnectivity matroid, and or some variants of them. For example, there is a recent result which says all these 3 matroids coincide when the embedding is to the moment curve, and then we can take this matrix and delete. We can delete 2 rows which correspond to the last vertex and 1 row which correspond to vertex n-1, and this will give us a full rank matrix, and we can try to do the same trick. Now, this will give us some weighted enumeration of minimally rigid graph. The weights will depend on the embedding. If we want to make this independence of the combinatorial type, we can have we can take all the permutation of the points and the average over it. So it looks that somewhere here there is an opportunity for an interesting analog of Kelly formula, and we know what we want. So the fantasy, I'm not sure we will realize it. We want to replace n to the power n-2, which is the number of labeled trees, by n choose d to the power n-d-1. And here we have even a generating function when we count level trees according to the vertex degrees. So this is x1 plus x2 plus xn to the power n-2, here pi xi. So this generating function gives you the number of level trees when counted. So a 3t is counted, a 3t which has degree d1 up to dn is counted with weight x1 to the d1, x2 to the d2, up to xn to the dn. And again, the fantasy would be to replace this expression by pi xi I from 1 to n to the power d times, here we take all the sum of all the products xi1, xi2 up to xid, where I1 is smaller than I2, smaller than ID, and the sum of all these products to the power n-d. So I think this is sort of interesting fantasy, I would say, that it would be nice to explore it. Okay, so I think let me stop here, and I'll be very happy to hear your questions or comments and to have a very small conversation. I think we have 5-7 more minutes, so we can talk about some of the questions we discussed in this series.
Thanks, Jill. Any questions or comments? As he said, we have 8 more minutes till 10 o'clock. That was the original scheduled time. So I can start it off, Jill. So you mentioned that, you know, Helly type theorems are have some connection to polyhedra, or did you mean that they have some connection to rigidity?
Yeah, I mentioned there is some connection of Haley type theorem to rigidity.
Mm-hmm.
So I can talk about it a little bit. Let me share the scene again. Okay, so there is a there is a way that Haley. Let me. So there was some topics that I didn't mention last time is there was the following conjecture or question by Perles and Kachalski, or Kachalski and Perles. And it was the following: if you have a collection given K1 up to Kn of convex sets, and suppose that no, say D plus, let's start with D plus. Suppose that no D plus 2 sets have a point in common, how many D plus 1 tuples may have a point in common? And the same question you can replace plus 2 by plus B. And they conjecture an example, the extreme example that they conjecture is the following: you take one copy of the full space, RD, and then n-1 hyperplanes in general position. So this is for the case D plus 2, and if you consider more than D plus 2, you put more copies of RD. So, for example, if you put K copies of RD, and the n-K hyperplanes in general position, then the number of D plus 1 tuples that have non-empty intersection. So, in order to have non-empty intersection, you have to make sure that you don't take all the D plus 1 sets among the hyper. So altogether, the number is n choose D plus 1 minus n minus K choose D plus 1. Okay, and now these numbers, okay, so these numbers are quite familiar for, you remember that if D is equal to 1, so n choose 2 minus n minus k choose 2, this is precisely kn minus k plus 1 choose 2. So this is the rank of the rigidity metroid. And indeed, also for this problem, some analog of the rigidity metroid, but not for graphs, but for hypergraphs, plays a role. So this is a place where I think the closest connection between metroids which arise in rigidity theory and their high dimensional analogs for hypergraphs or other form graphs, like the ones that Tay and Whiteley studied, are connected to Helly type theorem. So I think this might answer the question, or this is the beginning of the answer. But yeah. I expect more. In this case, the connection is very straightforward, and in some sense, it's even simpler than what we see for polytopes, where there are some other complications. But I would expect there are more. So these metroids, rigidity-like metroids, they occur in many areas, in several extremal problems in discrete geometry.
Okay, are there any further questions or comments?
Gil, could you please go back to the conjecture generating function for the rigidity counting of minimally rigid graphs?
Okay, so I should go back to sharing my screen. And I should say this, I would rather refer to it. Okay. So the conjecture is that, okay, the theorem about trees is that the number of labeled trees is n to the power n minus 2. And if you weight every tree with weights x1 to the degree of vertex 1, x to the degree of vertex 2, and up to xn to the degree of vertex n, then the sum of these weights is equal to the product of xi, x1 up to xn to the power n minus 2. So another way to say it is that the number of labeled trees where the vertex degrees are d1 up to dn is the multinomial coefficient n minus 2 with where you have below n, so it's n minus 2, d1 minus 1, d2 minus 1 up to dn. So this is the formula according to the degrees. And okay, and now the speculation is, now this is not a speculation about really the number. So I already checked that this conjecture is not correct. So the speculation is that something like this is correct. If you try to mimic the matrix tree proof in some appropriate way, and probably you will get some extra weights that I'm not familiar with, but what I want for some weights to get something like n choose d to the power n minus d minus 1 as the full number. And when you weight this minimally rigid graph or some other related metroid with vertex degrees, and perhaps with some further weights, which are these determinants that I don't know what they mean, you will get this generating function for the degree. So instead of the sum of the variables to the power n minus 2, you get the sum of you get this symmetric function, this symmetric function to the sum n minus d minus. Okay, so this is a vague fantasy, but I hope it's as clear as possible as a vague fantasy can be.
Okay, thanks. Sorry, I have a camera failure. So.
What?
I have a camera failure, that's why. Yeah, thanks for the answer.
Okay.
Oh, also, you know, my former student, Alan Fogelsanger, proved the generic rigidity of triangulated surfaces in dimension 3. Yes. I don't know if there's been much more on that.
So I think this Volcolam theorem is quite central in our in the connection between rigidity and the combinatorial of manifolds. This was quite a cornerstone. I think he even proved it not only for manifold, but for every minimal.
That's right, minimal cycles, that's right.
Minimal cycle, yes.
Yeah, it's a little ironic in the sense that in a sense, a manifold is more rigid than a sphere. A sphere is just rigid. A triangulated sphere is just rigid. And a triangulated manifold is sort of redundantly rigid.
It's rigid with some edges to spare.
Yes, exactly. Right.
But when you have to prove things, this is not always helpful.
Yes, that's right. Right.
Yeah, I should say that there are some variants of this theorem which try to deduce rigidity from some separation properties, which I think are still open. So even for two-dimensional simplicial complex with certain separation properties, which are perhaps more general or do not follow from this theorem, they are still open. Right. I think one application of the result you mentioned is for the proof that the lower bound theorem for two-coin Macaulay complexes, right? I'm not entirely sure. By Ran, so maybe Ran remember.
Yeah, that's right.
I don't remember if I met, so he's still in academia?
Pardon me?
Where is he now, your student?
I just looked online and he's a professor of dance. He was kind enough to put his thesis, make it available, but he was at Cornell for several years, and they sort of canceled the dance program that we had. And then he went elsewhere. The last I have seen online is at NYU giving lectures.
So, Professor, you mean dancing?
Dancing, yes, yes. He was an accompanist for the dancers at Cornell, playing the piano.
If you think about it, dancing has some connection with rigidity.
Yes, I could imagine.